Hi, welcome back to Statics 1. Today I want to talk about centroids. I want to talk about particularly centroids we find, or center of gravity, is kind of a similar term, of areas. And I want to show you an example of kind of what a centroid is. If we take a rectangular, basically two-dimensional object, and if we were to find the point on which this balances, there we go. So I found the center of gravity, or centroid. Essentially, it's the point where if you were to balance it, it would, or if you would place a point, this thing is going to balance on that point. Now, sometimes you're going to have centroids of irregularly shaped objects, and it's not so obvious where the centroid is. I think we all understand the centroid is going to be essentially the geometric center of this, halfway from the top and halfway from the side. When you have an irregularly shaped object like this one, it's going to be harder to find, but, well, this is more or less approximately the centroid of that object, of this two-dimensional curved shape. Now, why do we care about centroids from a perspective of statics? It really comes down to something we're going to be talking about, or you're going to be talking about next term when you take statics 2, or when you take it in the future. And if we have a rectangular beam, and what we're looking at here is the cross-section of the beam. So it basically goes off in that direction, back into the board. And I think we've mentioned before, and probably in the last time, we kind of talked about how it can have, if we had a downward force on this thing, and typically the beam would look like this, have two supports, and we have a downward force on the beam, and here we've taken the cross section through this thing, and what we find is that if we look at the pressure stresses on this thing vertically, so this is vertically Y, and this would be essentially the pressure, we find we have compressive stresses on the bottom of the beam, tensile stresses on the bottom, because this thing's being deflected down. And the upper side, we'd have compressive stresses. And somewhere near the middle, actually at the centroid, we're going to find we have a zero stress. So that's typically what happens. So we can draw it like this. So we have essentially positive compressive stresses, zero here at our centroid, and then negative stresses up the top. So here we have compressive stresses down here, getting larger, and basically the maximum compressive stress is at the bottom of the beam, and the maximum tensile stress is at the top. And at the centroid, providing that the area is homogeneous material, at the center, that's where we're going to have essentially a zero stress. And I guess I wouldn't put you could put a P, like P pressure, but typically we think of it as sigma for the stress, where it's essentially a force per unit area. Okay, so that's why we need to deal with, think about where centroids are occurring. If we only had rectangular beams, this would be a very short class. I wouldn't have much to talk about. But frequently we'll have beams, and they may be asymmetric. Obviously, I'm exaggerating in this case. But we are going to have the same sort of distribution, compressive stresses on the bottom, tensile stresses on top. And somewhere where the centroid is, that's where we have our zero stresses. And that's why we have to understand that, because that's going to help us to figure out what are these compressive stresses at the bottom, what are the tensile stresses at the top, and how do we go about designing this to deal with those stresses so that it won't fail, and we can have a well-performing beam with minimum deflection, and that reflects the material properties that we're dealing with. That's why we care about centroids. And we have talked about centroids before in another context. Remember, we talked about distributed loads on a beam. So here's our beam. And over here I'll put a roller, make it statically determinate. And we talked about what happens if we have a distributed load here, and how do we simplify that So we get the force and the moments basically identical to the original system, which is a distributed load. And what we said is if we put the total force, we added up this force and put it at the center of the distributed load, where the distributed load occurs, that's actually at the centroid or center of gravity of this portion of where the weight is being applied. And what we said is that centroid x bar, and that would be measured, well, you could measure it from wherever you want, but typically we measured from the left-hand side of the board. That would go to here. And we said that that's equal to the moment x times w of x dx. That's essentially the first moment, where w is our distributed load, and that's divided by x dx. Oops, excuse me. Divided by w dx. And this could be a w that varies over the length. Okay, so that's what we were talking about before. Oh, and this would be x bar is essentially a centroid of this area. Now we're going to talk about centroids of areas. So we need to think in 2 dimensions. And the way I would think about this is we have x over here and y here, and we have z obviously in the vertical direction. Now we're going to have some force downward in our x, basically the force will be parallel to z but in the xy plane, or acting downward and onto the xy plane. And it could be an irregular force, and actually I could draw it like that, or it could be, in fact, it could be like a uniform source but over a rectangular area instead of over a line. And then we would define this basically using 2-dimensional integrals. So I'm thinking about how to draw this, and I'll just draw it as an irregular shape. You have to sort of visualize this being on the xy plane. So how can I do that? Actually, let's make it I'm going to make it a rectangular shape. I think this will be easier to understand. Okay, so that's a rectangular shape on the xy plane, but these shapes don't have to be rectangular. Obviously, we deal with areas like this. Rectangle, well, that's rectangular. Okay, so now we define the centroids a little differently. Instead of using a single integral, we're going to have a double integral. So I'm going to do that over here. I want to erase this little picture here. And I'll write what the double integrals look like. And so x bar is going to be equal to double integral of x dx dy. So it's basically integrating over the area. Instead of integrating along a line, now we're integrating over an area. And we divide that by, again, double integral dx dy. And the hardest part is going to be determining what these limits are, how we specify the limits of our integral. If it's a rectangular area, it's easy. If it's not a rectangular area, it's going to be a little bit more tricky. And so y bar is going to be equal to, again, double integral. And I'm going to reverse this. You don't have to do this, but I'm going to write y dy dx. And then divided by double integral dx dy. And so this double integral is essentially, that is in fact the area. If you could measure that area. If you have rectangular, we obviously know it's just the base times height. If it's an irregular shape, then we're going to have to evaluate an integral. But that integral, then the denominator here, and this integral are essentially the same. All right, so what I want to do next is I want to show you how we evaluate these integrals for rectangular area, for triangular area, And then we're going to do it for a area. It's kind of not an irregular area, but an area defined by a function. And there are a number of examples in the textbook. They're not really, I don't think they're really as important as fundamentally as the rectangle and the triangle are. And we'll talk about later why that is. Because from the rectangle, we can evaluate. So if we know our centroid, we know the centroid of each of these objects is essentially at their geometric center, which is easy to find. And there are some kind of a simple rules for what we call the centroid of a composite object. In other words, get the centroid of the entire area. That's going to be a function of the location of the centroid of each of those points. And so we're going to talk about that in one of the future lectures when we talk about centroids of composite objects. Hi, okay, welcome back. So what I want to talk about now is, what I want to do now is to evaluate these integrals for x, to find the centroid of x, to find the centroid of I for three particular situations. One in which we have a rectangle where the base has a width of b, height of h. A triangle with, again, a base of b and a height of h. And then we're going to have this more complicated situation where one of the limits is defined by a function y equals x squared. This is one of a class of problems, some of which you're going to see in some of the assigned problems from the textbook. So I'm going to start with the rectangle. It's the easiest kind of situation we're going to be dealing with. And the rectangle, I think we all know already. If I were to ask you where the centroid is, hopefully you would understand that it's essentially at the center point, which would be at x equal half of the width, and the y value equal to half of the height. And I'm going to just show you, I'm going to go through the process of evaluating it formally using integrals and show you, in fact, that is the case. I want to make sure that we're actually recording. Yes, I believe we are. Okay, so we are recording. All right, so let's do this integral. And I'm only going to do x bar, then I'll kind of wave my hands and say, well, we could do the same and get y bar. So x bar equals, again, it's a double integral, x dx dy. And the only tricky part is to determine the limits in the integral. Although in this case, it's very easy. X goes from 0 to b, y goes from 0 to h. So again, it's the inner integral goes from 0 to b, the outer integral goes 0 to h. This is divided by dx dy. And again, the limits are the same, 0 to b, 0 to h. Okay, so that's where we're heading. I'm going to do the numerator first, and then we'll do the denominator. Although, in fact, the denominator, I think I'll basically just tell you the result because it's kind of very simple integral to evaluate. Although it's not written very cleanly. Let me clear this up. All right. I don't know why I did that. All right, so let's evaluate this thing. The numerator, and I'll write it again over here, 0 to h, 0 to b, x dx dy. And as we know, and I'll write this in the corner here, the integral of x to the n dx equals x to the n plus 1 over n plus 1. Okay, remember that's probably the most complicated integral we're going to be dealing with in this class. All right, so we're using that formula. We have basically x dx. We're going to do the inner integral first. We end up with x squared over 2. So the outer integral stays the same. We have x squared over 2 from 0 to b dy. And this is basically going to be b. We substitute in the limits, the first limit, and then we subtract of the x squared over 2 with 0 substituted in. Hopefully you're aware of that. So the 0 is going to be basically 0. Oh, I'll write it out. So we end up with something like this. 0 to h from b squared over 2 minus 0 dy. Okay, the 0 obviously goes away. Now we just have integral of dy, which equals y from 0 to h. And I'll write this here. And we end up with b squared over 2 times y evaluated from 0 to h. And if we introduce the limits, we end up with b squared h over 2. It's really b squared like that, h minus 0 over 2, and then we can write it out, b squared h over 2. All right, so that's the numerator in this term. The denominator is just, if you look at it, you should understand that it's just the area. We know the area of the integral, the area of a rectangle. And I think you could, if you see how this one's evaluated, you should be able to do this one as well. So I'm not going to go through the process. I will tell you that that integral, hopefully, this is not going to come as a shock to you, equals b times h, just the area of the rectangle. And then if we substitute these back into here to find out what our centroid is, we end up with x bar. We're going to take that one, b squared h over 2 divided by bh. And the h's cancel out, and we get rid of that 2 in the exponent, and we end up with b over 2, which is exactly what we expected it to be. That's the midpoint between the limits, because it's just a rectangle, right? And I will tell you also that y bar equals h over 2. Okay, it's going to be halfway up to the center, which is not unexpected. So usually for rectangles, we want to know the centroid. We know as long as they're not like rotated in some odd way, it's pretty easy to find the centroid of a rectangle. It's just the geometric center halfway from one side to the other. All right, so let's look at a triangle. And the reason one of the reasons I want to do this triangle is because it does introduce kind of a wrinkle in how we define these limits. And what we're going to do is this limit here, we're going to introduce basically a function of with respect to y that defines that upper line. So that's what we're going to do next. I'm going to erase this. We'll go back to do that. And once we finish this, I'm going to give you basically the general principle for finding the centroid of a triangle, because it's almost just as easy as the rectangle. Okay? So I'm going to erase the board. I'm going to pause this. Erase. Go back. Okay, so now we're going to deal with this triangle. And in this case, we're going to have limits defined by a linear function. And I already wrote it out here. Hopefully you'll understand this. So we have a base, b, height, h. And so the slope is going to be h over b. And because the y-intercept is 0, remember like y equals mx plus b, that b part, that y-intercept is 0. So we end up with just y equals h over b times x. And then we're just inverted it, and I also wrote it as x equals b over h times y. And this is what we're going to use as the limit for our integral, where we're going to go, we're going to take derivative of dx, basically going from this line over to this point where x equals b. All right, so let's show you what that means. So when we come up with x bar, remember it's in the numerator we have a double integral of x dx dy, and the limits of that. So x is going to go from, as I said, from b over h times y at the lower end. So that's what I'm going to put over here. b over h times y. And then at the other end, it's basically defined by b. And then our value of y is going to go from 0 up to h. Okay, so those are the limits of the integral. And that's really the trickiest part, the hardest part of doing this whole thing. If you understand how to do that, you should be good. What I always do is I write the inner integral as a function of whatever the variable is of the outer integral. So the outer integral is with respect to dy. So I make sure that the inner integral is defined as a function of y. So it's like almost like x inverse to find that line. And you will notice, if you want, you can look in the textbook, they always reduce these to a single integral. I think it's non-intuitive how they do that, and I don't encourage you to do it that way. I would encourage you to do it this way. But it's kind of up to you. If you really don't like this technique, you like the way they do it in the textbook, you like how it's described, by all means, go ahead and do that. All right, in the denominator, the limits are the same. We have, again, a double integral. Remember, it's going to be like integral of dx dy. And this is easy because this is just the double integral of dx dy is just going to be equal to the area of the triangle. So we know that the denominator is going to be b times h divided by 2. In other words, the base times height divided by 2. But what about the numerator? Numerator is not going to be quite as easy. So let's evaluate that. 0 to h, b over h times y to b. Those are limits. Make sure you know how to do that, because this is kind of the trickiest part. Once you figure that out, then the rest is pretty easy. Then we're going to have x dx dy. All right, integral of x dx. Remember, and I'll put it in here again, I had it before. If we have an integral of x to the n dx, it's just going to be equal to x to the n plus 1 divided by n plus 1. All right, so remember that. You see here the integral of x dx is just going to be x squared over 2. So unfortunately I wrote that there, so I'm going to have to write this here. Again, we have 0 to h, and then we have x squared over 2 from b over h times y up to b, and then we have our dy over here. And now we're going to substitute in the values of our limits into the x squared, and I'm going to write it over here. I think I have room. It goes from 0 to h, and b squared over 2, but I just introduced b into x squared, so we have b squared over 2 minus, now I'm going to take this whole thing, b over h times y, and I need to square all of it, and it's all multiplied times 1/2, b h over y squared, okay, dy. Well, I'm sorry, wait, I didn't do that right. b y over h. There we go. That's a little better. by over h squared dy. And now we're going to evaluate this integral, and it's going to be equal to b squared y over 2. That's this first part minus 1/2 b squared over h squared times y cubed over 3. And all of this is evaluated from limits of 0 to h. Okay, so I just took this term, I wrote it here, and then I integrated y squared. And when we integrated y squared, we end up with y cubed over 3. And now I'm going to introduce our limits. And again, the 0 limit is meaningless because 0 introduced to y is basically 0. Y cubed, 0 cubed is 0. So I'm just going to deal with that h limit. So we're going to end up with b squared h over 2 minus 1 over 6 times b squared h squared h cubed. So you can see that we have h cubed over h squared. So I'm going to cross that one out, and I'm going to cross out that 3. So we end up with just b squared h. So in fact, you see how b squared h over 2 minus 1 over 6 b squared h. So that's going to be equal to 1/2 is equal to 3/6. So 3/6 minus 1/6 is 2/6, which is 1/3. So we're going to end up with 1/3 b squared h. Let me make sure that's right. It is. That's perfect. And then that's good. So that is our numerator. B squared, 1/3 b squared h. The denominator, you can go through this entire process again, but we know that the integral, double integral of dx dy is just the area of, and again, this is a triangle, so just b h over 2. So the denominator is bh over 2. So I'm going to write the centroid here equals 1/3 b squared h over b h over 2. Yes, that's right. And it's finally going to be equal to 2/3 times b. So it's sort of interesting. Does not depend at all on the vertical height of the triangle, essentially for this particular triangle. I will tell you that the general formula, and I don't know where to put it. I'm going to put it right here. If we have, so this is the centroid, x bar equals 2/3 b for this particular geometry. But what if we have some general geometry like that, and we know the coordinates of the 3 points. In other words, this coordinate is x1, y1, and this coordinate is x2, y2, and this coordinate is x3, y3. In other words, when we know the coordinates of each of the points, the centroid, both for x and y, is just the average of the values. So x bar is going to be equal to x1 plus x2 plus x3 over 3. And y bar is going to be equal to y1 plus y2 plus y3 over 3. Okay, so the centroid is just the average of the centroid with respect to x. It's just the average of the x values of the coordinates at the points of our triangle, or the joints. And the y bar, it's the same thing, but in that case it would be the average of the y values of our points, of the 3 points defining the triangle. All right, so now we've done this for a very simple case where we had constant limits. We have another case where we have a limit. One limit is a line. And I want to show you a third case where we have a limit is essentially any other function, but it's essentially, we're going to do the same thing we did over here, where we had the lower limit being basically x as a function of y. We're going to do the same thing for this one here. So I'm going to pause it, and then we're going to come back, and we'll do that final case, and that'll be it for today. All right, so now I want to evaluate a centroid for a third area. And that's this one. It's a little more complex than what we were looking before. First we had a rectangle, triangle, and now we're going to do this one, where the upper limit of y, in this case, is y equals x squared. This principle is the same as we did it for the triangle. So in this case, we have x squared, x bar, in other words, x centroid. And it's going to be the same thing. We have a double integral x dx dy. Okay, and our x value goes from this line here to x equals 1. So I will put the 1 up here. But in this case, y equals x squared. We want to write the limit as a function of, we want it to be x, but as a function of y. So we just invert this. So this is going to be, if y equals x squared, then x equals y to the 1/2. So this is going to be x equals y to the 1/2, or the square root of y. Okay, so at the bottom here, I'm going to write y to the 1/2. Okay, and the y value is just going to go from 0 to 1. All right, so that is the numerator of the function that we need to evaluate. And then the denominator, we're going to have the same thing. Goes from y to the 1/2 to 1, dx dy. And I actually am less interested in actually evaluating this thing. It's just like pure calculus, and it can take a number of steps, and I don't want to spend a lot of time evaluating it. I will just tell you that the top is going to be equal to 1/4, and the bottom is equal to 1/3. And so the final result of x bar equals 3/4. It's less interesting actually what that number is, although we see that it's got to be less than 1, and we expect it to be, because the bulk of the meat of this thing is like over here, beyond x equals 1/2. We would expect it to be between x equals 1/2 and 1. So that is a result that we feel comfortable with. But what I want to show you now is how we do the same principle, but to evaluate the y centroid. And so the y centroid is the same thing. Y, in this case, we're going to write it a little differently. I'm going to write it the integral like this, and I'll do y dy dx. So in this case, we're going to be integrating, the first integral is going to go from 0 up to this point. So I'm going to go from 0 up to y equals x squared. And then x is going to go from 0 to 1. So that's how we do it. So hopefully, make sure you understand how to do this, of setting these limits. If you don't understand, then pause the video and think about it for a little bit and see if you can figure it out, or send me an email, talk to me, and I can help you understand it better. And then in the denominator, it's basically the same thing. 0 to 1, 0 to x squared, y dy dx. And again, I'm not going to evaluate this thing because it's actually not that hard. It only took me like 4 lines, but there's really no point in spending a lot of time doing this. But the denominator equals 1/10, and the numerator equal to 1/3. So we end up with 3/10 is our response. And it makes sense that it's less than 1/2, but not something between 0 and 1/2, because we expect the centroid to be down. Like if we're, like, you know, remember in the beginning when we were talking about how you balance, like if I were to turn this thing horizontally and put my finger there to try to make it balance, we would expect it to balance somewhere around here. So it's good that it's essentially 3/4 and 3 in that direction and 3/10 in that direction. Kind of intuitively makes sense. So make sure you understand how to do these problems. You will see other cases of many other kind of, this function might be something different. Sometimes they'll evaluate them not like that, but they'll evaluate them for something like that, where in this case it'll be the you just have to make sure you understand like how to set the limits, because that is kind of the trickiest part. And I won't say anything more about it, but I think this is a good general example, or particular example of a general class of problems. Hopefully you'll be able to understand how to evaluate those other problems as you encounter them. So we're going to stop it now. And the next step is we're going to look at centroids of composite objects, which we talked a little bit about at the beginning of this lecture. So send me emails if you have any questions. Otherwise, I'll see you in class.